All right. So as I was saying before, I've done the 2021 paper till, and I did that to 2019. Well, 2018, I believe. I think also 2017 is there. So, but this is the 2022 paper because I didn't do it. Right. So I guess we'll just begin. Number one, sodium can form ionic bonds with each of the halogens here. Which sodium halide is expected to have the highest lattice energy? What do you guys think is the answer for this?
B.
B. All right. So you're saying high. Okay, the fluoride. Why do you say that? What the question is? What is the question really asking, in a sense?
I interpret it as them asking, out of all of these compounds, which one would have the strongest bond based off its components.
Okay. So the lattice energy is okay. What does the lattice energy speak to? What is lattice energy? It doesn't have to be you personally who answers, but anybody could answer. What's lattice energy?
The energy required to convert 1 mole of a solid an ionic solid to its gaseous an ionic gaseous yeah
See.
to
Okay, it sounds a little bit disjointed. All right, but you look at the amount of energy required to do that. Therefore, the bond strength, right, will increase. Right, if the bond strength increases, the amount of energy required to break that bond will also increase. So we're saying that the lattice energy is speaking about polarization of a molecule. Right. So when the molecule, well, I would say the compound in this case, right? Now, when we look at the polarization of the, let me just let in this person real quick. Okay, so when you talk about a lattice energy, it could be due to the polarization effect, right? The polarizing power, right? That increases distortion of the electron crossing of the anion, right? In a sense, right? But here, the most electronegative element here would be fluorine, and the most electronegative element discovered will be fluorine, right? So we're saying that that would have a stronger relationship, right, with sodium, right, in its polarized state more so than it with iodine or bromine or chlorine, right? And we noticed that usually with halogens, their bonds, right, with other compounds tend to be stronger, right? When you ascend the group, so the weakest could probably be chalked up to being iodine. Then we have bromine and chlorine and fluorine. But you guys are saying that fluorine, sodium fluoride is the answer. Everybody agrees with B as an answer? Anybody has a different answer for this? No? Alright, it seems to me that nobody else had a different answer for this. Okay. To determine why a hairdresser stores her bottle
Sorry,
of
could you repeat
sodium,
the
go
answer,
ahead,
please?
sodium
Sir Never,
fluoride.
I was
Okay,
asking if you could repeat the answer, but I just saw that you circled it.
okay, no problem. To determine why the hairdresser stores her bottle of sodium, this is peroxide, right, in the refrigerator. A student sets up an apparatus shown below and recorded the volume of gas in the syringe every 30 seconds for 3 minutes. The activity was done in a dark room at a room temperature and in a dark room, and in a dark room at 5 degrees Celsius. Which of the following statements is not a possible assumption?
More gas is collected at a room temperature.
Sure. We can't assume that. Why would a hairdresser, well, why would a hairdresser store this in the refrigerator? I think you guys would have specifically looked at this compound. There are some things that like you specifically look at in chemistry. But I'm not sure if everyone else went through the same process. But peroxide itself, there's a reason why peroxide, when you buy hydrogen peroxide, you guys all seen a bottle of hydrogen peroxide before, right?
Yes, sir.
Yes, sir.
It's in this brown container, right? And it's usually to be stored in a cool place, right?
Yes, sir.
Okay, and we also see in the lab or within the prep room that certain chemicals, especially of organic organic chemicals, right? But chemicals themselves, some of them come in these deep red glass containers or deep brown glass containers, right? So they're really dark containers, and this is because there's some type of reaction, more specifically for most compounds, decomposition that occurs due to light, because light influences the rate of reaction for some reactions, right? Because remember, light is also something that influences rate. So what happens with sodium peroxide is that, sorry, not sodium, hydrogen peroxide, right, is that it tends to dissociate, it tends to decompose. The decomposition is usually increased due to light or temperature, right? So temperature can influence decomposition. So we could see that she stores it in a refrigerator where it would be dark. If the refrigerator is closed, that would be cool. Right, so what could be assumed from this, right, is that more gas is collected at room temperature. That could be assumed because the reason why she's storing it in the refrigerator is to make sure that her hydrogen peroxide doesn't decompose readily. Because why would you get a bottle of peroxide if you're just going to allow it to decompose? So we could assume that more gas will be collected at room temperature. It would decompose, right, faster at room temperature. Right. We could also assume that the light accelerates the decomposition of the of the peroxide. Right. Not only is that an assumption, right? As chemistry students, we would know that, right? The gas in the syringe is produced solely from that. As we can see how the experiment is set up, right? It should be produced solely from the peroxide. But the peroxide used is from the same stock solution as the hairdressers. That can't be assumed, right? That itself can't be assumed. We can't assume that, right? We do not know generally, right? So we have that there. Everyone's fine with that though?
Yes, sir.
Alright, let me just let in here real quick. Okay, so which of the following electron configurations is for the copper 1 ion? Give me a moment, go ahead.
C.
Okay.
A.
A? Huh.
C.
Yeah, I was what A. Why do you think
Oh,
A?
C.
Which two of the transition metal elements would have a force 1? Or somebody raising their hand? Go ahead.
Sir, I have a question.
Go ahead.
Sir, what is the answer C?
What is the answer C? Okay, could you tell me what the electronic configuration of copper is? Copper itself, not the ion. Go ahead.
Sir, so would that be AR 3D10 and 4S1?
3D10, 4, oh my, that's an S. It would be, okay, 3D10 and 4S1, right? So we're looking at that.
Sir, would it be 2? It would be 1.
Oh, force.
Sir, that'd be 1.
Force 1, that's what you said?
Yes, sir.
Force 1.
Yes, sir.
Okay. So it would not be force 2. So the compounds, the elements that we looked at, right, for the transition elements, right? There are 2 of them that has 4s1 within stable state. Which ones are those?
Sir, I would say copper and I think I can't remember the other one. Yeah, like she said.
Okay. All right. So hold on, let me let in this person real quick. Okay. So it would be 3D that 10 4s1. Right? So where does the electron leave from? Hold on. Let's figure out why you guys see as an answer. Where does the electron leave from for copper?
So if I transitional elements, first you remove it from the 4s orbital.
Right,
Then you
so
go on to the 3D.
and this is what type of ion? This is 1, right? Copper 1.
No, that nothing. That should not be that.
So isn't it A?
Ew, why is my thing black?
I can hear. Oh, the mic.
Nyla, everything.
Yeah, it's good. It's a good. It's better.
Okay, so shouldn't it be A?
Yes, sir.
Because if it is like that, right, it would be copper and chromium, if we could remember, would be alright with force 1. Right, so that is that. It would be copper and chromium. Let's look at this now. The enthalpy of solution of sodium chloride is. Alright, so we're looking at this. Go ahead. Somebody saying something. No? Alright. So the enthalpy of solution, how do you calculate the enthalpy of solution? How do you calculate enthalpy of solution? Solution is lattice energy plus dehydration, right? Let me just check in the chat. Is it not neutral? Wait, I don't know what you guys are talking about there. Can you guys hear me?
Yes, sir.
Okay, so
Yes, sir, just checking something.
alright. So we're looking at the enthalpy of solution. Generally, sol, it should be sol, right? It would be equal to the that's with the theta up here. Sorry about that. It looks like a gamma. Theta lat, right? And then it's gonna be added by the enthalpy. Hold on. Sorry about that. The enthalpy of hydration, right? Alright, so what would be your answer? What would you get from this?
Sir, I got +4.
Positive 4. Okay. Did you combine the enthalpy of hydrations here?
Yes, sir.
Alright. So you're going to combine the enthalpy of hydrations to get the overall enthalpy of hydration. And then you're going to add it to the lattice energy. So in short, you add up everything. And you should get, what do you say, -4? Does everybody agree?
Yes, sir.
Alright. If you disagree, you can state that. The overall balance equation for the reaction here would be what? So it would be that plus that would give us, okay. So what is it? I found it already. So what would it be for you guys? I'm waiting to hear. What's the answer?
C.
C. Okay. Nobody chooses A? Why not A? Alright. Okay, let's go with C then. Go ahead, what are you saying? Go ahead.
Because all you'd have to do is cancel out the 2 electrons and then you combine both equations. So you combine the reactants and the products.
Alright.
And
So it would be this and this, right? Would give you this and this, canceling out the electrons. Alright, the oxidizing agent here would be what? Give me one moment, I'll have to return. Alright. So, did you guys find the oxidizing agent? I had to step out from it.
I'm B.
B. Okay, are you sure?
I too yeah, because I was saying that if it's an oxidizing agent, that means it's being reduced, and reduction is the gain of electrons. And when you look at the half equation,
Okay,
it's gain electron.
so we're looking at that. Wonderful. Number 7, looking at this. The lines in the spectrum become closer together, or they convert at the shorter wavelength end of the spectrum because the what would it be?
I'll put D as in dog.
Okay. The difference in energy between successive levels is decreasing. Alright, so the energy of the successive energy levels. Alright, so you're saying difference in energy levels between the difference in energy between successive energy levels is decreasing as we go closer to the shorter wavelengths, right? So we're going this way, and we're seeing it's getting, the difference between the energies is getting smaller. That's fine. Which of the following gases is closest to behaving as an ideal gas under the stated conditions? What do you guys think it will be?
A.
A.
Okay. Hydrogen, alright, at high temperature and high pressure. Well, in this case, relatively low pressure. Alright, low pressure. So we saw these graphs when we were preparing for the paper too, I believe. Alright, so that should be fine. Number 9, which of the following structures correctly illustrates the coordinate bonding of boron trifluoride and ammonia? C would be the answer, right?
Yes, sir.
Okay. Number 10, deviations from ideal gas behavior generally occurs under conditions of
B.
Not hearing that.
C.
See? So you're saying that it would be, So you're saying C? C is high pressure and low temperature? Alright. That seems to be fine. Let me just have a look at the rest of them to make sure. So they do deviate at low temperatures and high pressure, so that should be fine.
Sir, could you repeat answer one number 6, please? I didn't get you.
Number 6 was B, iodine.
Thank you.
Alright, so let's look at this though. An iron nail was immersed in a solution of copper sulfate. When it was removed from the solution, it was coated with a layer of copper metal. Right? A second iron nail was immersed in a solution of zinc nitrate and removed, and this nail rusted rapidly. Based on this information, the rank order of the three metals in order of reducing power to most reactive to least reactive is
D.
D.
Yeah.
Most reactive
A.
is. Okay, we're hearing D and A as well. Alright, so let's look at this. An iron nail was submerged in solution of copper sulfate, right? And it was basically coated in copper metal. How does that distinguish the relationship between iron and copper?
Iron displaces copper 2 plus ions.
Okay.
Sir,
Go ahead.
I didn't say A. I'm not sure if it's me you're talking to, but I didn't say A. I said yeah. Like, yes, I was agreeing. So sorry.
Oh, okay. Alright. So we're looking at this. So the stronger reducing agents specifically, right? So generally zinc would be stronger than iron and iron would be stronger than copper, right? So we're looking at that as reducing agents, of course. And then it would be flipped for oxidizing ability. 12. Which of the following statements are true regarding the factors affecting ionization energies? So an increase in shielding effect decreases the ionization energy. An increase in the size of the let's look at 1 first. Is that true?
Yes, sir.
Okay. An increase in the size of a positive nuclear charge decreases ionization energy. That doesn't make much sense to me at all. An increase in the distance of the electron to be removed from the nucleus decreases ionization energy. 1 and 3 only. 2 generally won't make sense. Right? 13. Which of the following processes represents an oxidation reaction? Alright, we're looking at C, right? Everyone agrees?
Yes, sir.
Alright. The second ionization energy of calcium is that, right? Ionization energy is usually negative or positive. Which one? Is ionization exothermic or endothermic? And that means it should have a positive sign, right?
Yes, sir.
Okay, so if it's end on, we're looking at the second ionization energy. That means that calcium will already be in an ionic state. Alright, so we're looking at the 1 plus. Alright, so A would be the best answer. Copper 2 nitrate decomposes according to the following equation stated here. What is the volume of copper oxide formed when 18.8 grams of copper nitrate is heated up to constant mass at RTP? What would be the answer? You guys can go ahead. What is the answer?
Have to work it out first, sir.
Okay, yeah.
Certainly.
So how do you work this out? Yeah, but how do we work this out?
I would go about finding the mass of the copper nitrate. Not the mass, the moles, number of moles of the copper nitrate, and then you'd identify the mole ratio, and then afterwards, you'd find the volume of the NO2 using the RTP constants, basically.
What's RTP? Not what it is, but what's the value? What's the value of RTP?
24,000 cm cube by 24 dm cube.
Okay, I was about to do 24,000 cm cube, but like it makes sense just to leave it at dm cube. Alright, so it's gonna be 24 dm cube basically. Alright, so if we're looking at this, we say 18 grams of copper nitrate exists. What is the number of moles of copper nitrate there? Somebody tell me the answer, please. This shouldn't be too hard. What's the mass of copper?
So 63.
60 what?
64.
Relatively okay. 64. We can work with that value. So she got 170 something for this. Alright, the mass itself would be what, around 174, I think, grams per mole.
188.
Repeat?
188.
188. Okay. Okay, alright, 188. Okay. Let me see. So 64 plus that. Okay. Okay, guys, at 188. Okay. Calculated wrong in my head. Okay, so let's look at this. 188. So you're saying that it's 188 for the 1 mole, right? Or per mole. So how much moles is 18.8 grams? Let's do that quickly.
.1 mole.
And then that would be 0.2 moles, right? Of copper oxide. Do we want to reduce it? Or we want to keep the same mole ratio? Because if we use 2 moles, then that would be 0.2 moles used there. Right? Or be 0.1. Which one? We're saying that the mass of 18.8 grams would be 0.1, right?
Yes, sir.
Okay, so the number of moles within that is 0.1. So what's the volume, right? If, well, of the nitrogen oxide formed when that much of copper nitrate is heated on at constant mass, right? So it's gonna be a 1-to-1 ratio. Therefore, the moles of copper oxide would be 1-to-1, right? Well, it'll be 0.1, right? So what do we use to find this now? How do we find the constant? Well, how do we find the volume?
You multiply the mole by the 24 dm cube into moles per cube.
So the mole we're using is 0.1?
No.
Okay. What do we use?
0.2.
0.2?
Because they want us to find nitrogen oxide, so with the mole ratio, wouldn't it be 0.2?
0.2? Okay. You're asking, wouldn't it be 0.2? Delicia, would it be 0.2? Caroline, would it be 0.2? I want to make sure now. So you need 2 moles of copper, 2 moles of copper nitrate would be evolved from 2 moles of nitrogen oxide, right? Which technically is a 2-to-2 ratio, which technically is a 1-to-1 ratio. So what I want you guys to clearly state, right? Are we going to be multiplying the number of moles we found by 2, or are we going to leave it the same?
I think we can reduce it to a 1-to-1 ratio.
So you think you can remain at 0.1? Okay. So we're looking at the general reaction and how it works now, because it's a 1-to-1 ratio there for that here, right? But if you're looking at the others, it'd be, well, okay, it would be 1-to-2, and all right, so that should be fine. But can you reduce the reaction? Don't think we can here. But we're looking at the volume of nitrogen oxide formed when that amount of copper nitrate is heated. So that should be fine. What we're gonna do now is times it by 24, right?
Yes, sir.
So what do we get if we times that by 24? We'd get 2.4. But if we use 0.2 times 24, right, we get 4.8. But the general, what we're trying to figure out, you know, right? Isn't a 2-to-2 ratio the same thing as a 1-to-1 ratio?
Yes, sir, it is.
So I would believe that we just allow it to remain, and then we times it by 24 to get 2.4. Right, I understand the rationale of increasing the number of moles by 2. That would make sense in generally the case, but then we're going to have to reduce it to the number of moles to the lowest whole number ratio. So we're going to get 2.4, I mean. Because we usually work with that. Go ahead.
I'm not quite sure I understand, but isn't it copper nitrate to the nitrogen oxide and not the copper oxide?
Oh, did I say copper oxide?
Yeah. So it would be a 2-to-4, which would be a 1-to-2. So that's why I had multiplied it by 2.
Okay. I was reading it wrong. Okay, let's look at this. Oh, I see what you're saying now. So it's nitrogen oxide here, right, and the copper nitrate. So we're saying that, okay, it's a 1-to-2. Oh, I get what you're saying. So it would be 0.2 then that means that the answer is 4.8. Alright, I was looking at it wrong, my bad. Why does this not work here? Should work. Right, so it's a 1-to-2 ratio we're looking at. Right, so it's that to that. So if it was copper oxide, then it would be remain 1-to-1. Right, but that would be a 1-to-2. My bad. So the best thing, well, this is RTP, just showing you. Okay. Let's look at this now. Which of the following processes occurs as the cell operates? Which one is the cathode and which one is the anode?
Would that be the anode?
Would that be the anode? Interesting. Alright, we're looking at what is the EMF of this? Would it be a positive EMF or a negative EMF? Just asking. Of the overall cell.
I'll think positive.
Alright. Okay, so alright, so we can look at that. So we're saying that silver, being that silver has a positive EMF, I guess. Right? We're gonna look at that to say that what? Is silver have a more oxidizing power? Does it have a more oxidizing power than lead? Because one is positive and one is negative, so it's really easy to distinguish between them. Alright, so what does the EMF, alright, or well, the electrical potential say about oxidizing power? Or reducing power? We could move much faster than this, by the way. So we're saying that gold, right, itself here. So gold has a positive EMF. That means that gold, right, is a strong oxidizing agent, and it would be a weak reducing agent, right? And then lead would be a weak reducing agent generally, and then it would be a strong oxidizing agent, right? Comparing to gold here. So which would be the cathode and which would be the anode?
Gold would be the anode
Why do you say gold would be the anode?
because it's an oxidizing agent.
So you're saying that electrons travel from anode to cathode, that's what you're saying?
Yes, sir.
Okay. So she's saying that this would be the anode, right? So well, I don't even have to do that. Can't treat you guys like that. You guys know exactly what's going on, so I'm not going to be labeling anything like that. It's too simple. So you're saying that here would be the anode. The anode would be what charge? What would be the charge on the anode?
Positive?
Positive.
That sounds like a question. You sure it's positive?
Yes.
Sure. And cathode is negative. Sure. You sure you're not giving me a different type of electrode? A different type of cell? What type of cell is this?
Galvanic.
It's a galvanic cell, alright? So in galvanic cells, are cathodes negative?
No, sir, they're positive.
They're positive. Then why did you guys tell me that? Alright? We're saying if we assign gold to be the anode and lead to be the cathode, right? We should have something, well, let me fix that. That looks like this. The cathode is a positive electrode, please remember that, right? And the anode will be the negative electrode. I want you guys to remember that just in case any of the questions come. Right? So we have that there. So we're saying that electrons are traveling from here to here. So what will be happening with the salts now? Answer the question number 16. What's the answer?
C.
D.
Okay, so I'm seeing okay, C and B. Was that B as in boy? Alright. So let's look at this, right? Let's just try to eliminate all of them. So we say the nitrates and the potassium ions will migrate to what is new. B no nitrates and all right. So here we're gonna have here the nitrates will migrate towards the lead, right, and the potassium towards the gold. All right, so we have that there, and now we have here the nitrates will migrate towards the gold, right, and the potassium will migrate towards the lead. What is the focus of this? What is the importance of a salt bridge?
To facilitate the movement of the ions from both of the solutions.
Well, no. I would like to say no to that, right? Because that brings in a lot of inaccuracies. Go ahead.
Maintain the electrical neutrality.
Neutrality. So we want this to be neutral. That's what you're saying?
Yes, sir.
You sure? If it's neutral, then the electrons, the reaction stop. What is it? Okay, I get what you're saying about the neutrality, though. I understand the standpoint that you're coming from. But could anybody else give me another definition or another function of the salt bridge? What does salt bridge do? Alright, so the neutrality, alright. So to say I'll get the neutrality. Anybody else can add to that? So what does it do though? So it maintains neutrality via by doing what? Okay, I'm not sure whether or not you guys are following, right? So we're gonna have nitrates actually moving towards the anode, right? And we're gonna have our potassium moving towards the cathode, right? So we're gonna be looking at that specifically. So what would be the anode? The anode would be gold, so nitrates would move toward gold, and then the potassium ions to move towards lead. Do you guys agree with that?
Yes, sir.
Alright, so we have that there. So the let me see. The initial voltage is, what would be the initial voltage? What would be the initial voltage? Hello?
C?
C? Why is it C?
Show me subtract the 2 voltage demo that they give in a question.
Okay, so we have that to get C. So the question is asking what the EMF is. That's what you guys think it's asking? Alright. So you guys think it should be that. Everybody else agrees?
Yes, sir.
Yes, sir.
Okay. So C would be the best answer? Hello? C would be the best answer?
Yes, sir.
Alright. So we have that there. I'm going to have a look at this, right? I'm gonna have a look at it and get back to you guys with that. to clarify that C would be the best answer there. The direction of the electron flow is from... I kind of clarified it already. So it's going to be through the wire, right? And not the salt bridge. The buffer here, what's 39? And here is what? 7? What's it, 7? Okay, you guys... Wait, you guys...
Excuse me, sir.
Go ahead. 3.9, I mean. Go ahead.
For number 17, if AU is the anode, and if we use the formula to calculate the cell potential, would it not be cathode minus anode? So that would be A.
Minus cathode. Wait, hold on. I heard... Let me see what happened down here. I haven't looked at it though. Let me see. So the EMF across the cell, or the electrode potential across the cell, isn't it? It's cathode minus anode, right?
Yes.
It should be the more positive value minus the more negative value, right?
Yes.
And then that would... Isn't that addition?
No, but in the study guide they have they also have cathode minus anode. So I was thinking.
What I'm saying is that the cathode here, the cathode value would be what? 1.50, and then we're gonna minus
Isn't
the
that
negative.
the anode?
Oh, I'm looking at it the wrong. Okay, I didn't see it. I'm looking at it the wrong way. So this would be the anode. All right. Okay, so we're gonna have negative 0.13 minus 1.50. Okay, I seen that. So it should be cathode minus. You said cathode minus anode. Okay, hold on. Which one is the anode? Tell me which one do you think the anode is, right? The anode is what? On this
AU.
cell diagram, the anode. Right, so the
AU.
anode is AU. So we're gonna be minusing the positive A, right? So we're gonna be minusing that from 0.1, well, negative 0.13. Okay, what was the answer that you got?
A.
A.
Negative 1 point. No, wait a second. Wait, sir. The anode is AU, so that makes the cathode is PB. So minus 1.3. Yeah.
Okay. Let me just quickly do this. Do you guys agree with this though? Is there anybody who objects with the formula that we're using? Which is, the cathode minus anode. Well, minus the EMFs of them, by the way. Okay, nobody disagrees with it. 1.550. I mean, technically I don't have to put 0, but and what you say you got this. Okay, what was the answer? You got A? That's what you're saying?
I realized my mistake now. I mixed up cathode and anode. So yeah, I agree with your answer. Sorry, that was my bad. I apologize.
Because I'm confused at this moment. Right, I'm totally lost, by the way. Okay, right. Hold on. So
No, sir. I agree with your answer. You don't need to do it over again.
Okay.
I agree with you.
Right, but that's fine, but I just was lost a while ago because what? Give me a second. Because the answer I got, no. Give me a moment. So the anode should be gold and the cathode. Because everything moves from the anode, then the cathode. Therefore, if electrons move from gold, they should be that minus that. Okay. Should be fine. The buffer here, you guys understand how to get this? I did it ages ago though. It's in... It's in the well, I recorded the video of going through some of the past papers before. I had this question on it. All we have to do is just find the concentration, right, of the salt specifically, and then we do the Henderson-Hasselbalch equation. Do you want me to provide you with that equation? Go ahead, Leona.
Sir, where are those videos that you made?
Okay, I'll send them in the group. Because I did them that's why I'm saying, I did the videos ages ago, so I'm like, okay, that paper gone, moving on. And I see you guys answering questions, I'm like, the paper not gone. But okay, so I'll send them in the group. But then this Hasselbalch equation, let's do that. Because those papers I previously did, I just worked with literally everything on the paper. So I could just, not cancel, skip through everything and just mark the repeats. So the Henderson-Hasselbalch equation, we know it would be what? Somebody tell me what the first thing is. Henderson-Hasselbalch? Should be ruling off the tongue at this moment. What is it? Guys are giving me a tough time now.
So repeat it, sir.
What is the Henderson-Hasselbalch equation?
Base plus salt. Yeah, more base plus acid.
Plus acid. Wait, hold on. Okay, wait. That's what you found the buffer, but give me a second, right? That's generally no. The Henderson-Hasselbalch equation is the pH is equal to the pKa, right, plus the log, right? So it's usually like the negative log of something, but like it doesn't really matter for this case. So we can just log this, right? there's a simplification for it. So you just log that the concentration of salt ions over the it should be square bracket over the concentration of acid, right? And this is generally for a weak acid. We use a pKb when we're working bases, right? But since we have the pKa we have to use, and that would be the answer. What we don't have is the acid. Well, we have the acid concentration. What we don't have is the salt concentration, right? Which is our sodium benzoate right here. So we have the mass. So some persons would find the mass concentration and then derive moles and do the molar concentration. And then some persons would just find the number of moles within it and then give us the molar concentration. Whichever way you feel like to do it, we need the molar concentration of sodium benzoate. Right? Once we get that, we can just plug it in as the salt concentration and then we should get 3.9. Fine? If you guys want to do it for safety, just work it out. I'll give you a moment to work it out and see if you get 3.9. Just giving you guys a moment to do that. Work it out for yourself to make sure that it's true. So the pKa, as we know, is 6.4 times 10 to the negative 5 plus the log base 10, of course, right? Because I see somebody ln one of these, like ln, and no, right? So we can just lg, right? To the acid concentration would be what, 0.4, right? We need the salt, so we need to find the moles for that, right? We need to find that. So when somebody get the moles for it, can just tell me for me to drop it right here, please. 5. Sure. If you do that, what you're going to get?
I'm checking.
Okay. Thank you. I'm pretty sure it's 3.9. But if it works out to be a different answer, then I forgot. 5. I don't remember getting 5, but go ahead.
Sir, what decide that NA?
Oh, NA. What about what's mean by this self NA?
Is there a number below the NA in the sodium benzoate?
No, it should be a comma. It should be a comma. There's nothing else there. It's sodium benzoate, so by the chemical name, you should be able to get it. But... oh, never mind. You don't start organic chemistry yet, so what is that comma there? It's a pretty good benzoate. It's a weak base, therefore we use this one. Well, I mean, technically no, but we have pKa, therefore we use, well, we have Ka, therefore we use pKa, right? So we're looking at that. I don't know if anybody noticed the issue yet, but we have to use pKa in the formula, and I drop the Ka here. So notice that that is wrong. So we're going to have to find the pKa, and pKa is equal to what? The negative log of the Ka, 6.4 times 10 to the negative 5th power. So we need to get this value and plug it in here. Not sure if anybody realized that, but I'm sure you realize it now. Can't erase that. So I want the pKa and I want the salt concentration. So what is the pKa? Negative log that for me, please. And what do you get? 6.4 times 10.
4.19.
Repeat.
4.19.
Alright, 4.194. But we can just go to the 4.19. 4.19. What is the answer now? So it's a 4.19 now. So 4.19, right? Plus the log. Wait, where's the log? I can barely see what's happening. Then let's get that there. 5 over what? 0.4. What do you guys get for that? You guys getting 5.2 for this? There's something wrong. There is definitely something wrong.
You know what, sir?
Wait, I got 5.2 for this. So there's
what,
something for the pH. So there's something wrong with the concentration of salt. Go ahead.
3.88.
3.88, you got?
Yes, sir.
Okay, so probably I put in something wrong into the equation or into the calculator. Let me turn the light. I can't see anything on the calculator. Give me one moment.
So concentration
Alright,
for
so-
salt 0.2, you know, sir.
Oh wait, I didn't hear anything. I just came back. What are you saying now?
I'm saying the concentration for the salt is 0.2.
Yeah, alright. Because I really thought that 0.5 is really suspicious. But we're supposed to get 3.9. And for this now, we're supposed to get what, 1.0, alright, times 10 to the what, negative 7 or something like that. That's what we're supposed to get. And then that's why the answer is 7. Alright, so dissociation constant Ka for the above reaction is that. Okay, what will be the approximate pH? What is pH? What could we use for here?
H plus.
Alright, so the would be what, the concentration of H plus ions?
Would be negative. pH equal negative log times concentration of H plus.
Well, don't view it as times because log is an operation, so we just work with that, right? But I you know what you're talking about, right? But just don't say it as times. You may confuse some persons, right? But this should be fine. So what are we gonna do now? We're gonna find the concentration of hydrogen ions, right? So we know the pK to be that. Alright, looking at this amount of solution, so Ka is going to be equal to the concentration of, I don't know, I guess this is a halide, sure, and the hydrogen ion concentration up here. right? And we're gonna divide it by this down here. Right, so let me just reread the question once more. The dissociation constant, Ka, for the reaction is this. So we're saying that the Ka, let me remove this and put in the Ka. Right, so the Ka is 1.0 times 10 to the negative 12th power. Where's my thing? So it's 1.0 times 10 to the negative 12th power. Right? And that would be equal to this, the approximate pH, right, of this amount of that. Right, so what are we looking for here? What do we do? What do you guys suggest we do? So what we're saying is 1.0 times, well, 1.0, sorry, times 10 brought to the power of negative 12 is equal to whatever that is, right? Whatever the concentration of hydrogen ions is. Let me just check something real quick. It's a 1-to-1 ratio, so it should be fine, right? Over 1.0 times 10 to the negative 2. Shouldn't you get 1.0 times 10 to the negative 7? Or something like that? Well, let's figure it out. What do we get? Let me not do that. What do we get for the answer though? We're trying to find the concentration of hydrogen ions. So is it x squared we're looking for? Or is it x we're looking for?
X squared.
Sure. Everybody agrees that it's x squared we're looking for? Does everybody else agree?
Yeah.
No? Okay, yeah, okay. I mean, either way you take it, you're gonna probably find x anyways, but that's fine. So we're gonna find the total concentration that's happening up there. Everything is a 1-to-1 ratio, but sure. Alright, so we're gonna be looking for that then. That means that x squared is gonna be equal to what? We're gonna times both sides, right? So 1.0 times 10 to the negative 12th power times 1.0 times 10 to the negative second power. Laws of indices dictate that what should be the answer. Same base, different indices. What's the answer? We add, right, across the with multiplication. So we add the indices. What do we get? 1.0 times 10 to the what power?
Negative 14.
Negative 14. And when we, yeah, you're gonna get negative 7, as I said, right? So you're gonna get this times 10 to the negative 14, and we're gonna square root that to give x is equal to 1.0 times 10 to the negative 14th power, and that is 7. The pH is 7. Alright, moving on now.
Yes, sir.
Alright, okay, let's look at a wonderful diagram here. I know that the paper is blurry, give it a moment. Alright, so the graph above is depicting the titration of a pipetted amount of a
Sir, what was the answer?
7.
Oh.
Alright, so looking at that titration curve, what does that titration curve represent? What does it represent?
Strong alkali and strong base.
You didn't just say that, didn't you?
No.
Okay. So since you retract the statement, it's null and void. Alright. So there's a strong alkali and a strong acid. So that should be fine. Number 22, compounds P, Q, and R form an equilibrium as shown below. So we have this equilibrium here, therefore we need to find the units of K. So for the units of K, you can probably guess that, you know, whatever is happening here is not being good, of K. So this should be, what are we gonna get for the equilibrium? We're gonna have products over reactants, right? Brought to the power of their stoichiometry coefficient. Therefore, when we're looking at molar concentration generally, right, it would be mole per dm cube, right? Mole per dm cube, and then this would be squared, of course, right, divided by mole per dm cube squared times mole per dm cube. Right, the denominator, go ahead.
I'm gonna say a B answer.
Oh, okay. I mean, B is the answer, yeah? But just to make sure that everybody gets it, right? The denominator would give us what?
Mole per dm cube.
You sure? Wait, hold on. What the denominator? We're saying that we have mole per dm cube squared times mole per dm cube, and what we have as our answer is mole per dm cube. Now, for the denominator, what would the denominator give us?
Mole cube. What is?
dm to the negative 9th, right, power, right?
Yes, sir.
Over mole squared dm to the negative 6th power, and they will cancel to give us what? Mole 8 per mole dm cube. So B is the answer. Alright, let's move down. In a saturated solution of silver carbonate, well, equilibrium can be established between dissolving ions and undissolved salt according to the following equation. What is the solubility of silver carbonate at 20 degrees Celsius, given that the solubility product of silver carbonate is 8 times 10 to the negative 12 mole cube per dm to the negative 9th power? Solubility product, KSP is equal to what?
The concentration of the products.
Okay. So whether you are use H and X, A and B, K and W, it really doesn't matter. We're looking at the ions, the concentration of the ions within solution, right? That is what it's talking about. So you know that already. So the ions here would be this. Do we raise them to the power of the stoichiometric coefficient, or we don't?
We raise them.
Alright, so we're raising them. So it's going to be equal to what? No, it's going to be equal to Ag squared CO3 2 negative. Sure. Okay. Do we all agree with this?
Yes,
Everybody
sir.
agrees? Alright. So how do we find the concentration of these now? How do we get solubility from solubility products? Do we know the concentration of silver ions in solution? No?
No, sir.
So what we could say is that 8 times 10 to the negative 12 is going to be equal to x squared times x, which would be equal to 8 times 10 to the negative 12 power, that is a 2, my bad, is equal to what? X cubed? We could say that?
Yes, sir.
So x cubed is going to be equal to what? The cube root of that, right?
Yes, sir.
So what's the cube root? Let me shift this and cube root it to see what comes up.
We get 0.00200 30.
That's what you got?
Yeah.
Alright. So is that the correct way to do this? That's what I want to ask. No? Alright. Wait, you got 0.1? No? Okay, when I put this into my calculator, I get 2 times 10 to negative 4th power.
Huh? So we get 0.0002.
Wait, what did... That shouldn't be a problem. It's just standard form, probably. Probably the form in which you get the answer in. I think it should technically be the same answer. So, alright. So you guys believe it that is this way we should do it? If we do that, then the answer that we get, what would be the answer here? I don't like the fact that this is silent, and I would like to move on to complete way more papers than this. I'm not sure if it's that we like the confidence to complete them quickly, but it's taking a while to get a response. Is there anybody who disagrees with this method? Because this method is an iffy method. But does anybody disagree with this method of doing things? And if not, what do you think would be the answer based off of our answer?
Yeah, but isn't the answer that we got kind of far off?
Far off? Okay. So is this a method that we're supposed to be using?
No.
Alright. So, do we want to revisit the KP? KSP? What's KSP?
Solubility product?
Yeah. Well, okay, yeah.
Okay, is that what you mean? Right?
Yeah. No, it would be that, right? So that would be the KSP generally, right? And they would be brought to the power of their coefficients. Sure about that. So it would be that specifically. That should be fine. So in order to get this, we need to do what? So we're saying that we're looking for not the KSP, but we're looking for the solubility. Is there another way to do this? That's what I'm asking.
Not sure.
Not sure. Alright, so let's have a look at it again, right? So just to give you guys a little bit more time to think about what should be the right way of doing this, because my job is not to answer the question, you know? Right? It's to hear what you say and help with fixing it if it is not right. So we're saying that in a saturated solution of silver carbonate, the equilibrium can be established between dissolving ions and the undissolved salt. Right? So obviously it's that equilibrium it's speaking about. So we're looking at the solubility of the salt at 20 degrees Celsius, given that the solubility product is that. So how do we find the solubility from that solubility product? That's all we're looking for. Nobody?
Nope.
Like it's just okay. All right. So nobody can put anything here. All right. So when we're looking at getting K, well, sorry, X specifically, right? In the general reactions that we have, let's say that we have two silver here, right? Two silver here. Is it that we put it to the power here, or do we put 2 here? I want you guys to try this, right? I want you guys to try this. Eight times 10 to the power of -12. Try that and tell me what you guys get. What would be this? 2x cubed?
Yes.
2x cubed is now equal to 8 times 10, right, to the -12, right? And we're saying that if we cube root it, right, we're supposed to get back the answer that we said, right, which would be what, 2 point what times 10 to the -4. So what would be the answer?
Got 1.58 times 10 to the -4.
1.58. Hold on, wait, let me get my
What
calculator.
x when you want to find x?
Wait, if we cube root it, right? Okay, so I'm just asking, right? So if we do this, right, are we going to get 2x is equal to that answer? Asking that. So if I am to cube root this to get 8 times 10 to the power of -12, right, I am supposed to get 2 times 10 to the -4. Right? 2 times 10 to the -4. Right? So we have that there. And if I'm supposed to get 2 times 10 brought to the power of -4, right? And I divide that by 2, what would be the answer? It would be 1 times 10 to the -4. So if you look at it in that method, it is also a bit far from the answer, right? So what do you guys propose to be the method that we use? Just noticing that if I feel like we're gonna be like a bit stubborn when it comes to a question, right, I'm going to make sure you guys understand it. So I'm trying multiple methods, right? How do we get to this answer? Let me just put this on the screen. The answer would be x is equal to 1 times 10 to the -4th power. So do we in this event, right? Do we go to the closest answer? Do we choose the closest answer? Because if we just do it, right, as x cubed, we're gonna get 2 times 10 to the -4th power, right, which is closer to the answer B. But if we have 2x cubed, we're gonna get closer to the answer A. So which one is the right way to do it? how do you write the KSP expression? Okay, I think you're okay. So in the interest of time, right, it looks like we probably need to just move on. So the solubility product, how do you write the solubility product KSP, right, when there's multiple, right, ions within a specific solution, right? So if we have an example, for example, well, A, right, if we have A, so whatever thing, let's say AX, right, would give us an equilibrium, of course, right? A plus, let's say 2B, well, 2X, right? Should be 2X using that explanation, right? So we're gonna get 2X here. If we write the expression, what should we have? We're supposed to have A times X brought to the power of 2. Right? Is that the right way to write the KP expression? So if that is the right way to write the KP expression, right, then the answer that we would get is probably 2.10 times 10 to the, well, sorry, 2 times 10 to the negative 4th power, which would be B, would be the closest answer. Right? So it's not that it's far off, you know, right? It's off by a couple figures. And remember that when you're talking about solubility product and those type of things, the calculated is going to be different from experimental, well, or the actual, right? It's going to be off. If you calculate it, it's not going to generally get the same thing. So we'll probably go for the closest answer. So let me remove this from here. Are you guys following?
Yes.
All right. Because some persons tend to put the coefficient in front, right? And if they put the coefficient in front, they're going to get an answer that is a bit off. I was just trying to show that. If you put the coefficient in front, you get A. Right? But it should be around 1.6 times 10 to the negative 4th power. Does anybody have an issue with it though? Quickly before we move on to the next question. Does anybody have an issue with that though? No? Sure. Alright, we'll just move on. 24. The labels X and Y correspond to which of the following options? Is it C? We know hydrogen gas will be coming in at 1 atmosphere here, right? And then the solution would be 1 mole per TM cube, so it should be fine. Which of the following conditions will cause an increase in cell potential? Which one? Does concentration affect cell potential? Okay, go ahead. Thought somebody was saying something. I can't see the chat now, so let me go over here and look in the chat. So you're saying that D is the answer. So decreasing the concentration of zinc ions and increasing the concentration of copper ions. So we're saying that that will increase the potential, right? So we know that here now, right, would be A, B, C, anode before cathode, or A, anode then the bridge then the cathode. Alright, so we're saying that we're increasing the amount of ions, right, with the cathode specifically. Alright, and we're and we're decreasing the concentration of zinc, which would release the electrons. Are we sure that that will increase the cell potential? Sure. What do you guys think? You guys must have something to say. Jordy, what is it that you see? What would be the best answer here?
Sir, these are not my specialty, no, sir.
Sure? Sure about that. Okay, you're gonna encounter it way more, and in more complex forms. So you need to solidify it now or what somehow. Liana?
I'm still thinking on it. Sorry,
Still
I dropped off for a while, so I was thinking.
Alright. You need to know the effect of concentration, right? So the higher the concentration allows an increase in voltage difference. Right? So we have that. So
And we're saying D is the answer, or we haven't decided on an answer?
I was looking at D, so I want to know what you guys think about that. Go ahead right there. Okay, let me see what's happening here. What's the answer? So you guys don't know generally how this would work? So we're going to increase the concentration of the solutions. Right? Is that we increase the concentration? Right? Yeah, so we're going to increase the concentration of something. So in order to increase the cell potential, right, we're generally going to increase the concentration, right, that is using probably an electrochemical cell, right, but I'm wondering whether or not that would be used for galvanic cells. With galvanic cells, I know that you would have probably different volumes working. Let me check what this is saying. So this is a galvanic cell and not the other cell. So how do you increase the EMF of a galvanic cell? You'd increase the concentration of reactants as well, I would do believe. Right? So you're gonna allow the equilibrium to shift to produce more electrons. So if we're gonna do that, I believe that we're supposed to be increasing the concentration of both, right? But let's look at C, adding sodium hydroxide to no. Let's see. Adding sodium hydroxide to that should not be helpful. Alright. Decreasing the concentration of those ions and increasing concentration from copper ions. What do you guys think? I'm waiting on an answer now. Just saying. Are we sure this is the answer?
I assume it is.
Oh boy. Alright, so what we should remember, right? I'm just gonna give you it then. What you guys should remember about I think it would be for galvanic cells, right? If we decrease the concentration, right, of the anode ion, right, and increase the concentration of the cathode ion, both should give rises, right, in cell potential, right? So when you have an anode, if you decrease this concentration, you should have a rise, and if you increase this concentration, you should have a rise. Therefore, this is doing both. Therefore, that should increase the cell potential, right? I'm not sure whether or not you guys went over that, but that should be that. Here now, which of the following graphs, A, B, C, or D, correctly depicts E, A, right? So activation energy and the distribution of energy of molecules, right, in a chemical reaction of at 30 degrees Celsius and 60 degrees Celsius. So this is just a Boltzmann distribution curve. What would be the answer? What would be the answer here?
B.
Okay, that would be the answer. Alright, hoping that everybody sees that. Everybody sees it? Everybody understands? Everybody understands? Yes, no, maybe? Go ahead.
Sir, can you explain, please?
If I explain, I'm gonna have to teach Boltzmann distribution curves. What's basically happening here is that we have an activation energy here, right, as you can see, EA. If we increase the temperature, doesn't that increase the rate of reaction? Right? So what it's saying is that at 30, right, the area under the curve is here at 30. You can see that? So that's the amount. So that's the amount that we're working with here. But let's say if we increase the temperature, then the amount of molecules that reach activation energy should increase. So the area under the curve here at 60 should be larger, right? So here it has 30, which is larger. That should be wrong. Here it has 30 being larger, and the curve don't even draw properly, so that is wrong. And here I don't even know what this is representing, so that is also wrong. But B would be the best answer. Alright, B would be the best answer. Marine animals such as oysters and other shellfish rely on the slow precipitation of calcium carbonate to form their shells. Which of the following properties help this process? So it's going to be a greater ionic product. Okay, smaller solubility product can't have a greater solubility product. So a smaller solubility product, that means that 2 must be the answer and 3 must be out. The answer is A. I realize that the temperature that is just changed. What is the potential for a cell with the following reaction? EMF is what? Cathode minus anode or anode minus cathode?
Cathode minus anode. Cathode minus anode.
Alright. What is the cathode? Look on your formula sheet that you should get in your exam and tell me what the cathode is. I mean, you should know generally. We're looking at a metal and a non-metal here, but still tell me. Non-metals tend to gain electrons, right? And metals tend to release electrons. Metals tend to store positive ions, therefore you guys don't even need a formula sheet, right? Or that paper thing, the data booklet thing. I don't even know what that is. But yeah, so you know that the zinc generally should be around probably the cathode, right? The cathode, and bromine would be the anode. So what we do, we take the cathode and we add our minus, add our subtract.
Can you repeat your question? The last part I didn't quite get that.
So we take the cathode, right, the cathode value, and we add our subtract from the anode. It's subtracting, right?
Yes, sir.
So what value would it be? Would it be positive or negative? The cathode, what would be positive or negative? That's the E naught of the cathode. Would it be positive or negative? Because we're already saying that we're minus, so that is out. This is going in a forward reaction, right? So therefore it should be positive. You guys understand number 27 though?
Yes, sir.
It's a bit off though, but if I show the process, it's a bit off, but we have that there. 29. The answer should be what? 430, or is it 29? What's the answer that we have here?
C.
Alright. So we're saying that this full reaction is 860, right? And we conserve energy, right? Energy doesn't really fluctuate that much. So we're saying that if we half everything, it should be half of this. That should give us 430. Cytochrome oxidase is an enzyme needed for the living systems, in living systems, for the efficient metabolism of food in order to obtain energy. Traces of copper in the diet are needed in order to catalyze this reaction. Copper can catalyze this reaction due to its ability to
B. Changes oxidation state.
Alright. And this is one of the same reason why iron is found within hemoglobin, because iron can change its oxidation state. Right? 31. The tip of a piece of clean platinum wire was dipped into powder, right, of a powdered white solid, then held in a Bunsen burner. A flame, shown a brilliant brick red color, right? So it's brick red. Which of the four metals would be present within that powder? The red. What would it be?
Sodium.
Sodium. Sure?
Calcium.
Alright. So is it sodium or calcium?
It's calcium.
Calcium. Sodium is more of an orangish, right? A bright orange, right? Right there, both. Calcium is more of like a deep red color. Strontium is crimson red and stuff like that. So you have to really look at that properly. Number 32. I plan to move really quickly now, because we spent too much time on this paper so far. Right, so this is acidic, this is basic, and this is an amphoteric oxide. But do you guys want to choose aluminium as well? Because I think there's an iteration of this question where it says amphoteric, and it would make much sense. But aluminium could have basic or acidic character. So would you guys include one in this?
No, sir.
No? Okay, so if you guys don't include it. On the previous papers, right, I went through and I was looking at it. I was like, okay, it has basic character and acidic character. So probably on the previous papers that I did, you probably say like I chose all of them, right? But it's based on how people interpret it, because I was having a conversation with somebody and they're saying like, okay, even though it can be basic and acidic though, it should be both. So you're saying that they won't choose it. So I get that on that thing. So if you see on previous papers I put all of them, it's because, right, I just off the bat assume that, okay, it can be basic or acidic, so anything should be the answer, right? But they're saying that, okay, based on the logic, they don't want to put basic because it looks like it's basic alone, which it isn't. But I understand that, right? So you can move on from that. 33. Which of the following reagents does not aid in the identification of X? What will be the answer? liberate hydrogen. Go ahead.
C. Dilute nitric acid.
Nitric acid. Sure. Sure. Are you sure about that?
No.
Just asking, you know. I'm not telling you that it's wrong. I'm asking. Go ahead.
Well, based off like tests that my teacher was showing, I've never seen nitric acid really being used to distinguish between two things. So
Okay,
that's
so
my behind it.
Okay, so it's not normally used there. Alright. 34 calcium carbonate decomposes at a lower temperature than that of barium carbonate, because I was also looking at this question as well. This question was a bit iffy as well. Go ahead.
So what was the answer for the previous one?
Nitric acid, dilute nitric acid, because it would be another solvent. I mean, it's fine if it's a solvent, right? But we're trying to see how that would work, because even if we find a halogen here, or it won't be a halogen, it's positive, it's a metal ion. Okay, so nitric acid won't work generally, or it shouldn't work. Alright, so we have that there. Okay, so let's look at this. Calcium carbonate decomposes at lower temperatures than that of barium carbonate. Alright, so I was looking at this and saying that, okay, calcium carbonate itself, its oxide should be more stable than the barium oxide, right? So I was looking at that. And the calcium ion is larger than the barium ion. That is not true. Alright, so I was looking at them and removing the stuff that doesn't make sense. The standard enthalpy of formation of calcium oxide is less negative than that of barium oxide, or the lattice energy of calcium oxide is larger than that of barium oxide. So what do you guys think would be the best answer here? Please don't allow the question to go on for too long.
Sir, someone
D.
is saying D.
Okay, somebody saying D, and I heard somebody say D a while ago. So D. Alright. Was it a 2 plus KB? Hold on. Give me a moment. That's a 2 plus ion. Okay, that should be fine though. Okay, so back to this. So you're saying that the lattice energy of the oxide is larger than that of barium oxide. Alright, so we're looking at the stability probably. Alright, so we have that there. 35, which of the following properties belong to group 2 elements, right, of the periodic table?
D.
Ajin dog?
Yes,
Yes,
D.
sir.
Okay. So low densities technically is right. Technically. Low densities are important. Nope. Here as well. They have high melting point and high electrical conductivity, sure. But the low density is relatively to something though. 36, which of the following compounds would produce the lowest pH? The lowest pH when 0.5 moles of it is bubbled through 1 liter of water. Which one will give you the lowest pH?
A.
You sure?
Sir, between A and B, because they said that the oxides of non-metals are acidic. So if it's acidic, that means it would be a low pH. But I'm not sure why it would be A over B.
Okay. Okay. So if we look at it, right, sulfur dioxide should produce sulfurous acid, right? While sulfur trioxide should produce sulfuric acid. So there's a difference. So this would be the strongest. Alright. So A would be the answer there. 37. The hydrogen halides are gases produced when samples of these sodium halides react respectively and treated with the concentrated sulfuric acid. Which of the following will undergo oxidation?
Sir D.
D. So you're saying chlorine and bromine only will undergo oxidation. So the gases are produced when, okay, so the gases are produced, which are the gases undergo oxidation, right? We're looking at, what are we looking at here? We're looking at strength, right? The strength of their stability. Oxidation is a loss of hydrogen, right? So which one could lose hydrogen more readily, right? Definitely hydrogen iodide would be an answer, right? Hydrogen iodide would definitely be an answer. But hydrogen bromide can be oxidized as well. So I would go with C. Hydrogen chloride won't be as easily oxidized as everything else. I don't believe so. Alright, everything is good? Everything is good, everyone?
Yes, sir.
Just want to make sure. Which of the following elements have the highest electronegativity? Sulfur is closest to fluorine on the periodic table. Right, that not all of them, but it's the closest noble gas. Right? That is closest to that. Looking at this now, 39. The sharp increase from copper to zinc is caused by what? What is the difference between copper and zinc? Is the answer A?
Sir, would the explanation be that copper prefers to have the 4s half full?
Okay.
I'm asking.
You're asking. Oh, I thought you were supposed to be telling. Alright. It could be. I'm not gonna give a complete answer. Unless you tell me an answer, I'm not gonna give a complete answer. So the difference would be in the 4s orbitals because it's gaining an electron, right? So it should be fine. Here, no. Which of the following factors is responsible for iodine having the highest boiling point? What's the answer?
A.
You sure? Sure?
I would say D, sir.
Okay, you said D. So halogens actually get a bit stronger, as you know. Right? So van der Waals forces between molecules increase down the group. Well, okay, alright, so it would be D. D would be the better answer. We'll look at what would increase the boiling point, right? So we know that boiling and those type of stuff are due to the breaking of intermolecular bonds. Right? Intermolecular bonds between the two different things, right? Between two different molecules. So if we're gonna say that there's more intermolecular interaction, that means that the boiling point will increase. So we're saying here that we're increasing van der Waals forces, so it should be fine. Elements can be classified by their response to externally applied magnetic fields as diamagnetic, paramagnetic, and non-magnetic. I'm not sure if I went through all of these with you, but which one would show the highest degree of paramagnetism?
Sir, which module is commander?
Oh, this is module 3.
Oh.
It's fine. You guys should have gone through it. Go ahead.
I think C.
You think C would be the answer? Alright. Okay. Okay, alright. C. Anybody else has an answer?
I would say B.
Okay, I hear B. What is paramagnetism? What is paramagnetism?
The magnetism with one or more unpaired electrons.
Okay. So you're saying that scandium is the most paramagnetic? So it is paramagnetic, right? But is it more paramagnetic than the others? Nobody's answering. So you need at least one unpaired electron in the ground state. So we're looking at that. Cobalt though. Does cobalt have an unpaired electron in the ground state? Hello? Guys?
Yes, sir.
So which is more paramagnetic? Scandium or cobalt?
Sir, cobalt.
I say B. Cobalt.
Why?
Oh, because scandium only have one and cobalt have three. I think, maybe.
Okay. Cobalt would have the stronger one. So the answer is B. Alright, what is diamagnetism? What does that speak to? Okay, so let's look at this, right? What is the answer to this? So we have the solid. We're gonna have lead ions being shown with potassium iodide to give that yellow precipitate. For A, we know generally, right, that there's gonna be a white precipitate, which is soluble in excess, right, for zinc ions. And for lead or aluminium, we're gonna have B, right? So it's generally insoluble, right? So this is around early or late fifth form chemistry, right? So that's fine there. And then the configuration for cobalt is cobalt 2+, may I add? Or might I add? What do you guys think the answer would be? If you know it's cobalt 2 plus, what immediately comes to mind? Which one? A?
A. A.
A. Right? So you don't
Yes,
have
sir.
yeah, you don't have to care about anything else. You know that cobalt is only one up spin within its 4s. So you see if it's a positive ion, then you know that this is gonna be empty. So like you don't have to count anything. 4s of empty. So A. So that is the end of that paper. It took way too long to complete this, right? So we're just gonna speed run everything else.